Okay, hey, so now on to the integral, which results in an inverse trig function. Let's recall how this stuff works, okay? So just recall finding the derivative of an inverse trig function. Where does that come from? Well, we sort of introduced it after the chain rule. So recall, basically, from the cancellation equations, we have that f of f inverse of x is always equal to x. Okay, and then we could take the derivative of both sides and implicitly in particular. So this would be on the left f prime of f inverse of x, and then times from the chain rule the derivative of the guts, which would be f inverse prime of x, and on the other side we just have 1, and then we could solve for f inverse prime, right? So f inverse prime of x would equal 1 all over f prime of f inverse of x. Okay, so then if we're given this function y equals sine inverse of x that we want the derivative of, and we notice then x will equal sine of y, and then we also notice that implies x prime will be cosine of y. We can kind of use that formula to figure out the derivative of y sine inverse of x. Y equals sine inverse of x, right? So y prime then will equal 1 all over this x prime thing, so that f prime is basically this guy here. So it'll be cosine of f inverse, which is sine inverse of x. And then we could use triangles to simplify that, right? So go over to your triangle. In particular, noting the guts of this cosine function, sine inverse of x. So x is kind of the angle we're worried about. So if the output of sine is opposite over hypotenuse, then the input of inverse sine is opposite over hypotenuse, so opposite over hypotenuse. And then the third side from the Pythagorean theorem, you could solve for that as just be 1 minus x squared. So the cosine of that angle is going to be adjacent over hypotenuse, which is going to be square root of 1 minus x squared. Okay, so in particular, if you have sine inverse of x, its derivative will be 1 all over the square root of 1 minus x squared. And also, we recall Mr. Stroop had us memorize the derivative for arctan as well. It should be 1 all over 1 plus x squared. Okay, so if we know the derivatives, then we know there has to be this integral, right? So then the integral of 1 all over the square root of 1 minus x squared dx will equal sine inverse of x plus c. And then right here, the integral of 1 over 1 plus x squared dx will equal tan inverse of x plus c. Okay, so we know that. Now the formulas we want to use are going to be a bit more general. So in particular, so this next section, we're introducing the integrals. Integrals basically that we'll be working with. And of course, we can derive these integrals just from the basic formulas that are given above, but we're not going to get carried away. So anyways, the first integral, du all over the square root of a squared minus u squared, which is going to be the sine version. It's just instead of 1, we have a general a squared in there. That will be your arc sine, if you will, or sine inverse, whichever way you want to write it, of u all over a plus c. And then for the tan function, tan inverse function, it's du all over a squared plus u squared, which will be 1 all over a tan, arctan or tan inverse, whichever, of u all over a plus c. Those two I want you to have memorized. So more stuff to remember memorize. And then the third one, you don't have to have memorized, but you should be familiar with. Du all over u times the square root of u squared minus a squared equals 1 all over a times arc secant the absolute value of u all over a plus c. Okay. Okie dokie. So let's dive in here and do some integrals. And just to the side, I believe the cosine version is just a negative involved. There's just a negative involved, so you really don't even need it. Okay, and likewise for the tan, I believe. But off the top of my head, I don't remember. Okay, I'm sorry. I don't really use those very much. Anyways, let's get into the exercises and see how we do. Right. So here we go. Dx all over the square root of 9 minus x squared. Okay. All right. So we want to get it in the same form as the first formula I gave you, and you can kind of see, yeah, it is in that form. So a is 3, and then the u is just the x. So we could use the formula without much rigmarole. If you don't even really need to rewrite it. The answer is just going to be sine inverse of x over 3 plus c. So not much fanfare there, just there it is. All right, so let's look at another one. Let's just call these examples from the book. We don't need to put numbers on them. Example, so this guy 12 all over 1 plus 9x squared. Okay, dx. Okay, so what form is it? You know, well, it's the tan. Tan's the only one that doesn't have a square root on it, so it must be a tan form. You can factor out the 12. The a value is going to be 1. The u, though, maybe that's a little harder to see. So let me rewrite it. Factor out the 12. I get 1 all over 1 plus 3x squared dx. Okay, so yeah, the u is actually 3x, and then to get it into our form, we need to do the regular, you know, figure out the differential and all that jazz. So du will end up being 3 dx, so dx will be du over 3. Let's box that off. So I end up with 12 times the integral of 1 all over 1 plus u squared times du over 3, and now it's perfectly in our form, and we can just apply the formula. So 12 over 3, you factor out the 1/3, you get 4 times the integral of basically du over 1 plus u squared. So that'll be 4 times, using the formula now with a equaling 1, you have 1 all over 1. So the weird thing about this formula is you always have to remember there's that 1 over a in the front. Right, there's this thing as opposed to, whoops, there's this thing as opposed to the arc sine, which doesn't have anything in front of it except a 1. So in this case, it won't matter. You'll just have 1 over 1, which is 1 anyways. And then you'll have arc tan, or tan inverse, however you want to write it, of u all over a. So that plus c. And then back subbing, this will be 4 tan inverse of 3x over 1. Plus c, and then that's the end of the story. Okay. Okay, let's move on. So this one example, we kind of have a binomial in the place of our usual u variable. So here we go. 1 minus x plus 1 squared. So this form is the arc sine form. It's the only one with a radical, and you have 1 minus some variable expression squared. The a value is clearly 1 in this case. It's just the u is a bit different, right? It's x plus 1. The du is just dx, so no issues there. So we can rewrite the integral of dx with the du now, all over the square root of 1 minus u squared. It's in our form. So that's going to be arc sine, or sine inverse feed rather, of u plus c, and then back sub. So get sine inverse of u, which is now x plus 1, plus c. Okay. Let's keep carrying on. Another example. weirder and weirder expressions in for u. This is dx all over x times the square root of 1 minus the ln of x squared. Okay. It looks like it's a inverse sine, but sometimes after you do your substitution, things cancel. Because I mean, it kind of looks like a secant, but it also kind of looks like an arcsecant, but it also looks like an arcsine. It looks like an arcsecant because it has that variable in front of the radical. But the terms are out of order. So usually you'd have the x part first and then minus a squared. And this is like a squared minus u squared. So let's do our substitution and see what happens, right? So let u be the ln x stuff, and then du will be 1 all over x dx. And then, of course, dx, if you wish, is x du. Let's box that off. So doing our subs, we have dx. Well, we're going to have to rewrite the dx, right? We'll factor that off to the side. So let's just put 1 over 1 all over x times the square root of 1 minus u squared. And then dx is now 1 over, it's x du. Dx is now x du. So the x's are going to cancel out, right? And that's what we need to get through the gate, so to speak. And we're left with the integral of du all over 1 minus u squared and the square root. And yeah, that's an arcsine, okay, with a value equal to 1. So using the formula now, we have sine inverse of u all over a. So it's just u and then plus c. And then back subbing, we get sine inverse of ln x and then plus c. Okay, let's look at number 15, or sorry, just random example numbered. Dx all over the square root of x times the square root of 1 minus x. Okay, this one is really weird. You don't really see a squared term in there, so it kind of looks like an arcsine. Maybe it's an arcsecant, I don't know. But if you rewrote it and then do a u sub, it's kind of obvious. So what is the u going to be? It's the square root of x, okay, because the square root of x squared is just x. Okay, so I'll let that be my u. So u is x to the 1/2. du will be 1 all over 2 root x dx, and then solving for dx, you get 2 square root x du. Okay. And then you'll see a nice cancellation. So this will be the integral of, instead of dx, we have 2 square root x du. You can put it off to the side. I'll just put it in the numerator. All over the square root of x times the square root of 1 minus u squared. So the square root of x's are gone. We needed that. You can factor out the 2. And then you just have arcsine integral sitting there. Okay. Right, so this would end up being then 2 arcsine of u all over a. A in this case is 1. If I did not notice that before, a is 1. So we have u all over 1, which is u plus c. And then back sub 2 arcsine of square root x plus c. Okay. Let's look at another guy. I haven't seen anything except arcsines. So let's look at this guy. dx all over x times the square root of 4x squared minus 1. Okay. So clearly, or at least I hope it's kind of clear, this guy is not an inverse tan. It could be maybe an arcsine, but it doesn't really have the u squared minus a squared form on the inside. So it's more likely to be the secant inverse or the arcsecant. Okay, so I'm going to and if it's not obvious, let me rewrite it so you can see what u is going to be. The 4x squared is the same as 2x squared minus 1. Okay, so my u is going to be 2x. Then my du, of course, is 2 dx. In other words, dx is just du over 2. One other thing is I kind of have to rewrite the x in the denominator. So if you do go ahead and rewrite it at this point, what do you have? du all over 2 all over x times the square root of u squared minus 1. Okay, I didn't clear out the x's, right? But you could go back here and use this formula to rewrite x. So x will equal u over 2. Okay, so we can rewrite this expression as du over 2 all over u over 2 times the square root of u squared minus 1. And then you can kind of divide out the 1/2. So there's a 1/2 in the numerator and a 1/2 in the denominator. So it's just going to leave you with du all over u. Or you can multiply top and bottom by 2 if you rather think of it that way, times u squared minus 1. So you multiply this by 2, the 1/2 will go away. This by 2, the 1/2 will go away. Okay. So once you do that, it's obviously, an arcsecant. So you have u times the square root of u squared minus 1. So that's going to end up giving you 1 all over a. Of course, a in this case is just 1, times arcsecant of the absolute value of u all over a. Seems like all of our a's have been 1 so far. I apologize for that. Hopefully the next problem will change that. Okay, so back subbing, I get arcsecant of the absolute value of u, and of course that's 2x, the absolute value of 2x, and then plus c. Okay. Let's look at maybe a little bit of a harder one. So we have the integral of x squared plus 3 all over x times the square root of x squared minus 4, and then dx. Okay. So how the heck am I going to pull this one off? It has elements of an arcsecant, but that's not the whole story, right? Because that numerator kind of screws it up. So what I'm going to do is undo finding the common denominator and adding the numerators of the common denominator, right? So you're going to butterfly it. Okay, so you end up with the integral of x squared all over x times the square root of x squared minus 4 dx, and then plus the integral of 3 all over x times the square root of x squared minus 4 dx. So that second integral is going to become an arcsecant, and the first integral is probably just a u sub of some sort. Okay, so note that first integral, we have an x squared over x, which can be simplified into just x over the square root of x squared minus 4 dx. And the second guy, you factor a 3, and then you have dx all over x times the square root of x squared minus 4. So yeah, that guy's an arcsecant. The first guy requires a u sub for that stuff inside the radical. Du will just be 2x dx, and then of course dx is du over 2x. So you have a 1/2 floating about. So the integral of x all over the square root of u times dx, which is now du over 2x, plus this guy, 3 times, and the a value here, we have an a of 2. Finally, that's a little bit different. So using the formula, it'll be 1 all over a times arcsecant, or secant inverse if you'd rather, the absolute value of u, which in this case is just x, all over a, and then plus c. Okay, and then that first integral, we're ending up with a 1/2 to be factored out. The x's cancel, thank God, thank goodness. U to the negative 1/2 du, and then plus 3/2 secant inverse of the absolute value of x over 2 plus c, and then integrating u to the negative 1/2 plus 1 is now to the positive 1/2, multiplied by our reciprocal, 2, plus 3/2 secant inverse of absolute value x plus over 2, plus c, and then finally back subbing, 1/2 times 2 is just 1, so we have x squared minus 4 to the 1/2 plus 3/2 secant inverse of absolute value of x over 2, and then don't forget this is a family, so put in that plus c. Okay. Alrighty then. Next, so completing the square with these guys. Complete the square. So for example, you'll see things like 2x all over x squared plus 6x plus 13 dx. And you really can't do a u sub here, so you're kind of stuck there, but you can complete the square. Just remember, when you complete the square, you have to add in this b, as in beta, all over 2 squared, and then immediately subtract it. Beta all over 2 squared. Okay. All right, so in our case then, b over 2 will be 6 over 2. Sorry, my 6's look exactly like b's. So I try to write it a little nicer. 6 over 2 is really the same as 3, so I have to add and subtract 9. Okay, so this will be the integral of 2x all over x squared plus 6x plus 9 minus 9 plus 13. And then it's going to take on, I think it takes on the form of I don't know. So let's take a look and see what happens. 2x all over x plus 3 squared, then negative 9 plus 13 is plus 4. Yeah, so it kind of has, and I mean kind of, has arctan, but not really, because it has x in the numerator. So what you got to do then is maybe a u sub on the x plus 3. So du will just be dx. And then you'll see u squared plus 4 in the denominator, and then du, and then a 2x. And we have that pesky x in the numerator we need to get rid of, but you can do that using the u equation. So I'll have x equals u minus 3, and then that'll do the trick. So 2 times u minus 3. But then I need to butterfly, okay, into 2 new integrals. So I'll have the integral of, and if you distribute, 2u all over u squared plus 4. So I'll need to do a u sub on that guy, and then plus, or rather minus, in this case, minus the integral of 6 all over u squared plus 4, which is arctan integral. Okay, so let me do a u sub on the first guy, or rather a z sub. So z is u squared plus 4, and then dz will be 2u du, and then du will be dz all over 2u. So I'll end up with, and I can factor out a 2 if I wish, but I don't know. I guess I don't really need to, because it's going to cancel out, right? So it's 2u all over z times du, which is dz over 2u, right? So that's what I was talking about. The 2 u's will cancel. Minus, which with an a value of 2, I just use my formula for arctan now. It'll be 6 times 1 all over a times arctan of u all over a plus c. And then this will be the integral of 1 over z dz minus 3 tan inverse, I need the back sub as well, x plus 3 all over 2 plus c. And then so ln, that's our integral from the previous section, ln of the absolute value of z minus 3 tan inverse of x plus 3 all over 2 plus c. Then back sub for z, ln of u squared plus 4 minus 3 tan inverse of x plus 3 all over 2 plus c. And then back sub for u, which was x plus 3. Okay. So that'll equal ln of the absolute value of x plus 3 squared plus 4 minus 3 tan inverse of x plus 3. 1 over 2 plus c, and that'll do it. Okay. Oh, wow, that's a hard one, huh? Okay. So just sometimes you'll be pedaling along and you'll see something and you're not sure what it is, and you'll have to complete the square maybe or do a substitution. Sometimes these integrals look like it's going to be one type and turn out to be another type, like this one kind of maybe looked like a secant inverse but turns into an arc sine. Yeah. These are the integrals you need to have memorized, so get those guys memorized. And yeah, that's about it. Okay, so thank you for watching, and we will see you next time.